In this video, I have a few MCQ practice for static equilibrium. The first one being this one. If you need to pause, read. Essentially, you have a beam that is 40 kilograms. It has a length of 5, and you got 2 strings attached to it. The question wants you to find the tension on the left side that supports the plank to keep it horizontal. So here, it's important that you kind of visualize the diagram and then label what is expected of you. I'm just going to call the string on the left side here T, because that's what the question is looking for. Why there are 2 strings, I'm actually going to put my pivot through the second string on the right here. Why would I do that? Because I don't know what it is. I don't need to know what it is. So if I'm just a little clever, I put the axis rotation through there, or aka my pivot. Because any tension or any force that runs through the pivot generates no torque because it's missing an R value, right? So therefore, I'm just going to go ahead and label the rest of my work here. The weight of the beam, it needs to be placed at the center of the beam. So this purple arrow here represents the weight of the beam. The mass of the beam is given as 40 kilograms. So all we have to do is take 40 kilograms and times it by 9.8 meters per second squared to find the weight of the beam. All right, so here, it's important that you understand how to measure the R value in your torque function, because torque is equal to force cross R, but the R must be measured away from the pivot or the axis of rotation. So while the diagram gives you this 3 meters in length from the second to first string, or from the left string to the right string, I need to actually find this little length here in the purple, which is 0.5 meters. So if you think about it, half of the beam is 2.5, and this is 3. So the leftover would be 0.5, right? Because 2.5 plus 0.5 is 3. So it's important that you find this little segment and not just use 3. Again, you need to go back to definitions of F and R and then apply correctly. So here I'm just going to set my counterclockwise torque equals to clockwise torque. And it doesn't really matter whether you put clockwise on the left side or counterclockwise on the right side. You just have to identify the appropriate force and the R value here. All right, so from left to right, if I'm looking at my own particular notation here, the pivot is along the second right string, which I don't care for what it is because I'm just going to put my pivot there that eliminates that particular unknown. So here, F of G is to the left of the pivot, which is actually going to cause this beam to rotate in the counterclockwise direction, while tension is going to point up on the screen. Pulling it upward will cause it to rotate clockwise in this particular example. So here on my left, F of G, the way the beam will cause it to rotate counterclockwise. And how far is it from the axis rotation? Is 0.5. Again, don't let diagram fool you. You need to stick with what is needed in order for you to be successful in these types of problems. Okay. On the right side, the torque that generates a clockwise direction, that's going to be T. So if you visualize, here's the pivot, and once again in the system here, if you pull upward on the left side, it'll actually cause the beam to rotate in the clockwise direction. Well, the force is 3, and how far is tension away from the axis of rotation? That's going to be a length of 3 meters. And other than that, really here you can just simplify your stuff. F of G, once again, is just mass times gravity, as I mentioned earlier. That's just 40 kilogram times 9.8 meters per second squared times 0.5, which is the length away from the axis of rotation of the pivot. And then T here is our unknown, and how far is T away from the axis of rotation, which is 3. So if you simplify this on your calculator, the software T divide both sides by 3, and then voila, you get about 55.6 Newton. That's going to match choice B. Okay, so let's move on to the next one. Here in the next one, if you need to read, essentially you have a before and after scenario, and in the initial scenario, you're given a mass M that's placed some distance R away. You push down to keep it horizontal or balanced. In the second scenario, you have the mass of 2M, so the mass is double. However, you're decreasing the distance away from the fulcrum to a third, and then the question asks you what is the force that's needed for you to apply in order for you to keep it stationary. So essentially, I'm just going to do really just 2 scenarios. So here, I'm just going to draw this. This is the weight of the box on the right side of the fulcrum. And then here is the force being applied downward. The problem states is the person is pushing downward. I'm just going to call that F. And really, again, this is a static equilibrium problem. Nothing is moving. The beam is horizontal, aka balanced. So counterclockwise torque must equal to clockwise torque. So here, I'm just going to say that F times R, because the fulcrum is your pivot. How far is it from R? Excuse me. How far is F from the fulcrum? That's just the distance of R. So here my work, I just said F times R, and then the weight, if the mass is going to generate a clockwise torque, well, F of G by definition is just mass times gravity. In this case, the box is labeled as capital M, so I'm just going to say capital M times G. Well, how far is it from the fulcrum? Once again, the diagram calls it R, so I'm just going to call it R. As you can see here, R cancels out on both sides because you're just multiplying by R. So we can simplify this particular expression down to just the force needed is equal to F of G, which makes sense, right? You're putting a weight out here and you're also pushing at the edge. If the distance is the same, then the weight must equal in magnitude in order for it to be equilibrium, right? So this makes sense to me. Like the force that's applied by the person must equal to the weight of the box. Otherwise, the system will not remain in balance. But again, that's because R is the same. Well, now if you move the box towards the fulcrum, doubling it, however, at the same time, the distance from the fulcrum is decreased. So you have to find what this F is. So here, I just drew the weight of the second object again, which is 2m, and that's I'll call it F of G nu. And then likewise on the left side, I don't know what the force that the person needs to exert, which is essentially what the question is asking for. I'm just going to call that F nu. So here, I'm just going to set up the same physics really, but all you have to do is just make sure you plug in the right values for distance and weight here. Well, what is F nu? I don't know what F nu is. How far is F nu away from the fulcrum? Well, the fulcrum hasn't moved compared to the first diagram. It's still in the center. So from the fulcrum to what F nu is still a distance of R. So that's why the left side, really, the R stays the same. On the right side, though, well, the mass double. So F of G is going to be 2m now times G times the distance away from the fulcrum, aka axis of rotation, which is now 1/3 R. So I'm just going to write R over 3. So once again, you see there's an R on both sides. You can cancel that. So really, you can say the F nu here is just 2mg divided by 3. Okay. Well, what happens now? You just have to now identify what are constants, right? If you pay attention to my work for the first scenario, we stated that F is equal to mg. Well, here in the second expression, you have 2mg divided by 3. Well, mg is the common term, so I'm just going to highlight this, and then I'm just going to replace it. So wherever mg is, I can just say mg is F because that's a true statement. So instead of writing mg, I'm just going to replace mg with F. So voila, we can have an expression for F nu. F nu is just 2/3 of the original force needed. Okay, and that matches with choice A. That's 2/3. All right, here's the last one in this video. You have some sort of beam. There's a string. There's a sign, and it wants you to find well, what the string is, the horizontal force and the vertical. So here, this is static equilibrium. So I'm just going to go ahead and set up once again. Net torque in the counterclockwise equals clockwise. The string here is going to be pointing towards the wall to the left here. I'm just going to go T. Well, T is the diagonal, so it has to have Ty and Tx. Ty is just T sine theta, theta being 36 degrees. Then Tx is cosine here because the angle given is touching the horizontal axis. So Tx would just be T cosine of 36. All right. Other than that, I'm just going to identify the rest of the forces. The weight of the sign is given. I'm just going to call it F of G sign. And then the beam, the weight of the beam is also given. So it says the café's outdoor sign weighing 260 Newton. And then the uniform beam has a weight of 156 Newton. So once again, FG sign here is going to be 216. And then F of G for the beam, I'm just going to place at the center of the beam again. And that's given as 156 Newtons. So keep that in mind. So here, I'm just going to apply again. Counterclockwise versus clockwise. Pulling on the beam using the vertical Ty component will cause it to rotate counterclockwise. And how far is it from the axis of rotation? If you look, Ty is a distance of 1.36 away from the axis of rotation. So on the left side, that's it, right? Well, in case you're wondering, well, what about Tx? Tx parallels the beam. So when you do torque, you're looking for perpendicular components relative to the beam. Here, Tx is parallel, so it actually generates no torque. So while there is a force, it produces no torque. So we can just leave it out here. So don't touch Tx for this particular problem. Well, what's generating the clockwise torque? Well, you have the weight of the sign. You also have the weight of the beam, which will both naturally produce a clockwise torque. So because they're in the same directions, we add. Well, F of G of the beam here is placed at the center of the beam, but the diagram tells us that the beam itself is 1.71 meters long. So you need to place the F of G at the center of the beam, which is half of the distance. So in my work, I put 1.71 divided by 2 because it needs to be half. Okay. Other than that, you're going to add the weight of the sine, because the weight of the sine will cause this beam to rotate in also in the clockwise direction. Well, how far is the sine away from the axis of rotation? It's actually the whole length. So all you have to do is really try to be consistent with the diagram. From the hinge here all the way to the edge where the sine is hung, that is a distance of 1.71. So hopefully you kept up with my second line there. As you can see here, now it's really just a plug and chug, right? Well, the question asks you to find what T is, what the horizontal force on the wall is, and what the vertical is. So I'm just going to break up Ty into T sine theta because it's a true statement. So here now I have T, and everything else really is just a number, right? 156 times some coefficient is just a number. 216 times 1.71, that's just a number. And the only unknown here is just T. So I'm going to clean this up a little bit. If you punch in calculator sine of 36 times 1.36, it will give you roughly 0.8. It's like 0.799 something something. So I just round up to 0.8. And then 156 times 1.71 divided by 2 will give you about 133.38. And then likewise 216 times 1.71 gives you about 369.36. As you can see, these are just two coefficients on the right, so we can just combine them by adding them. You add them, it gives you about 502.74. On the left side is 0.8t, so the solve for t, divide both sides by 0.8. So you're going to get that about to be 628.43 newtons. So if you scan out the answers right away, you have A, B, C, D, E. The only answer that resembles the outcome that I just got, 628, is about 629, right? Well, I see 629 in choice B. I also see 629 in choice E. So I need to differentiate between B and E. Well, here I'm just going to go ahead and focus on the horizontal, and hopefully I can find the horizontal and just pick the correct answer. Hopefully two of them matches. Well, the system's at rest, so I can set up Newton's second law in the horizontal direction. And I'm doing this horizontal next just because horizontal force is given as the next statement, okay? I know my AX is 0 because the system's not moving, but if you think about it, right, well, in the X direction, there's only TX pointing left from the tension in the string, so therefore the hinge here is going to exert an opposing force in the X direction in order for the system not to accelerate in the X direction. So I'm just going to call this Fx from wall, whatever you want to call it. So here, the net force in the X direction equal to MAX according to Newton's second law. But if you look at the diagram, you have Fx pointing to the right, which is needed. Otherwise, you would only have one force pointing left, which would imply that the beam is going to accelerate leftward, which is not doing, which would be kind of weird. So here, I'm just going to write Fx minus Tx. Fx pointing to the right, Tx is pointing to the left. So I'm going to say Fx minus Tx is equal to 0. And then from here, I can just really move Tx to the right side. So negative Tx is going to become positive Tx. And then keep in mind, I'm trying to find F horizontal. So really, I'm trying to find Fx here. So one of the Fx has to match with the choice B or E. All right. So to find Fx, all I need to do is find Tx. But Tx is, once again, T cosine of 36. If you kept up with the geometry earlier. So Tx here, where I'm circling my cursor back and forth, according to this particular triangle, Tx is just T cosine of 36 is the angle given touches the x-axis. So here, T we already calculated, and the first part of the problem here, which is 628.43. So I'm just going to place that in, and cosine of 36 is just a value in a calculator. So you plug in 628.43 times cosine 36, you'll get 508.4, which matches, well, which is closest to choice B, because choice E said is 670. Which is kind of crazy. All right. Anyways, I hope that helps. Stay nerdy. Don't be whack.